So in this part, we will be looking into virtual memory. Basically, we will see how operating system manages main memory and how virtual memory helps in operating system using the physical memory or rather main memory in an efficient way. So let's ask ourselves a simple question. Does a user process has to be completely loaded before it could run? More specifically, let's say when we have Hello World program, which has code segment, data segments, and heap segments, so on and so forth. When we give the program to the operating system, does all the pages or all the contents needs to be in the main memory before the program could run? Not necessarily, right? This is actually if wasteful if the operating system tries to do that, because at any point a process will access only small amount of memory at any given time. It doesn't access the, like, when, for instance, when a process is running a function, most of the times it will be using the memory that belongs to that function and also the stack variables. Okay, it need not access, like, it will not access the code or rather memory that belongs to other regions of the code, right? So this is called reference locality. So specifically, for instance, Donald Knuth's observation is that 90% of the time program spends in 10% of the code. Okay. And there is also significant locality in data references. That means most of the times programs access certain regions more, or rather, like, there is asymmetry in the access patterns of a program. That means a program doesn't access all the data regions uniformly. Rather, uh, the accesses to data references, they change. For instance, if a process is running in a function, it may access certain regions of heap more than other regions of heap. Similarly, when the process is executing some other function, it may access other data regions, right? So this is called principle of locality. So at any given time, not all the regions of memory will be accessed by the program. So we need not store all the pages or all the contents of a process in the main memory. That means in the physical memory. So how can we do this? Virtual memory, or rather virtual address, allows us to do it. So the key idea is, because we maintain the page tables, we can like, which actually maintains the mappings, we can actually store the physical page or the contents of the page either into physical memory or into disk, which is which we have enough of, right? So disk is usually cheaper. Of course, it's slow, but it's usually large. Like, for instance, I have disk of like 1 TB compared to RAM of like 4 GB, right? And however, accessing disk is slower. So virtual memory provides this amazing opportunity for the operating system to store the page either in the physical memory or in the disk. Okay, this is possible because of this amazing page tables. Because of the one level of indirection, we were able to store a page either in the main memory or in the disk. Okay. And virtual memory is so this virtual address provides the illusion of virtual memory, and according to the process, entire virtual memory is actually in the main memory, right? So as a process doesn't know whether a page, either it is in the main memory or it's on the disk. It doesn't know it. It's the operating system that knows. And the way operating system manages pages in the main memory, it's called demand paging. What it means is, operating system doesn't load all the pages that are needed by the process in the main memory at any given time. No, it will only load the page when it is needed by the process. Okay. So when the page is not needed by the process, operating system can store the page on the disk. So this process of bringing the page into the main memory and taking it out of the main memory is called swapping in and swapping out. And this process of loading the page when it is needed, it's called demand paging. So let's see how demand paging works. So if all the program code, if like not all parts of the program, if it is loaded in the memory, how does the program run? Or rather, what happens when a program tries to reference a virtual address or a byte that is not in the main memory? Okay, so how can we detect this in the first place, right? Because if it is in the disk, it cannot be accessed, right? So the only way a process can access certain memory is if it is in the physical memory, right? If however we don't however operating system doesn't uh, put all the contents of the program in the physical memory, so there should be some way for the operating system to know when a process requires certain virtual address or like certain page. So in order to notify operating system when a virtual address is needed, hardware provides some support. So basically what happens is in every page table entry has this extra bit called present. So this present bit indicates whether that particular page is in main memory or not. Okay. So if that bit is not set, that means that particular page is not in the main memory, it's in the swap space or rather on the disk. So whenever the present bit is not set and when process tries to access that particular virtual address, page fault occurs. The page fault occurs, it's indication for the operating system that a page that is needed by the process is not in the main memory, right? And what can operating system do when the page fault happens? So it needs to take the page from the disk and put it back into the main memory, right? We'll actually look into an example how exactly page fault gets handled in the operating system after a couple of slides. Okay. So because of this present bit, hardware provides an opportunity for the operating system to capture or like to allow getting the pages from the disk into the main memory. So as I mentioned before, so now each page table entry has an additional bit called valid bit, which indicates whether the page is present in the main memory or not. So we actually looked into malloc in the previous part. Here, what happens is, let's say when the process calls malloc, like before malloc, the virtual address is not assigned. Okay, the virtual memory is not given, or rather there are no page table entries for that virtual address. So after we call malloc, virtual memory is given to the process. That means we create page table entries. However, we are not there is no physical page corresponding to this virtual memory. We just created a virtual memory by creating valid page table entries. Okay? However, here we don't set the valid bit because there is no corresponding physical memory for this virtual memory. We just created virtual memory after malloc. Okay, we did not assign the physical pages yet. So when the first access happens, or when the process actually tries to uh, read or write the address that is written by malloc, that's when the physical page gets assigned, and then the valid bit corresponding to that page table entry gets set. So that is when the real memory gets assigned. So before malloc, there is no virtual memory. After malloc, we give the virtual memory, but there is no physical memory corresponding to that virtual memory. But when process tries to access the virtual memory, that's when we will assign physical page or physical memory. So this is called demand paging. So how to capture the first write? Because we want to assign physical page during the first access, right? So that means we need to have some way to capture the first write or first read uh, to a virtual page. So this is done by the present bit, like the valid bit that we saw before. So whenever a process tries to access virtual memory or virtual page where the valid bit is not set, so in this case, a page fault gets triggered. It's a trap into the operating system. So operating system, the trap handler kicks in, and it will assign. That means like we actually get the corresponding physical page. We assign the corresponding physical page. We update the page table entry, and then we restart the uh, process from that faulting instruction. If the virtual memory is not allocated, we segfault as we saw before, or else we allocate the physical page. So let's see how demand paging happens. So let's say uh, we assign the virtual memory. However, there is no physical page corresponding to that virtual memory. That means corresponding to that virtual page. And process tries to access that particular virtual address. So what happens is when it tries to access, we get a page fault. So, and the virtual memory subsystem gets kicked in. It will find the corresponding page from the disk, and then it will find, and also because it needs to bring the page back into the main memory, it has to find a physical page, any of the physical page where it should bring back, right? Let's say VM subsystem finds a physical page. However, that physical page is assigned to some other page, some other virtual page. So operating system now has to, now operating system will actually save the page from the physical, from that particular physical page to the disk. Okay, and then it will bring the requested page into that particular page. Then it will reset the virtual address corresponding to the swapped out physical page as invalid, and then it will update the faulting address, like the PTE that corresponds to the faulting address, to be valid, and it will make that virtual virtual it will make that page table entry point to the physical page that it just swapped in. Okay, so this is how demand paging works. So note that one thing that we need to see is, so VM subsystem, like the availability of physical pages, like I mean, the physical pages may be assigned to some other process. However, VM subsystem can actually take the page away from a process, or from a different process, and swap the page out, and then it can update the corresponding page table entry as invalid, and it can go on. So maintaining, having this page table provides this amazing opportunity, or rather trick for the operating system to provide this illusion of having all the pages in the main memory, whereas in reality, only few pages will be in the physical memory or the main memory. Most of the pages will be on the disk. So operating system will bring back the physical pages from the disk whenever they are needed. So this is the essence of demand paging. So in summary, so when a page fault occurs, or rather when the physical page corresponding to the virtual page is not assigned, is not allocated, or it's swapped out, that means when the page fault that's one of the reasons why the page fault happens. So when a page fault happens, so first operating system will have to find one of the unused pages, unused physical page, or even used physical page, that's also fine. So once if the physical page is used, so it needs to swap out the physical page into the disk, and it should also update the page table entry corresponding to the selected physical page to be invalid. Okay, and it also should update the TLB entry. How will it do it? As we saw in the previous lecture, it just invalidates the corresponding page table entry, corresponding TLB entry. Okay? And then now, after saving the contents of the selected physical page, it needs to load the requested page from the disk into the selected physical page, and it will update the faulting page table entry and its TLB entry to point to this new physical page. and it will restart the faulting instruction. So this is in summary what happens in on a page fault. Okay. So in order to make faster, like in order to enable faster page fault handling, operating system needs to know which physical pages are assigned to which processes, right? Because whenever it selects the physical page, it needs to update all the page table entries to be invalid, right? So it needs to maintain a data structure which maps physical page to the process IDs and the virtual addresses to which it is mapped. Okay. Does this sound familiar? Inverted page table. If you like in the previous lecture, we saw inverted page table. This is one of the uses of inverted page table where physical page, where we store the mapping from the physical page to the virtual virtual addresses and the process IDs to which the virtual address belongs. Okay, we store the inverse mapping of the page table entries. So in the next lecture, we will look at how demand paging happens, and we'll see more details about memory management.